Welcome everyone to this episode of MIDI, the MIDI Infrared Discussions webinar series. I'm Simone De Liberato, and together with Vincenzo Giannini and Stefan Meyer, I will serve as host today. After last week theory talk about intersubband polaritons, today we go back to Phonon-polaritons, and we are very honored to have with us Professor Jérôme Faist. Professor Faist is a professor at the ETH Zurich. He has made many seminal contributions to physics and photonics, including the invention of the quantum cascade laser. And today he will tell us about his works on the realization of a phonon-polariton laser. Some practical information. The talk will last roughly 45 minutes, following time for questions. Please note this webinar will be recorded and it will be eventually shared online, including questions. Thank you very much. Please, Jérôme.
Thanks a lot, Simone. It's really a great pleasure to be invited here, and I would really very much like to thank you and also Vincenzo and Stefan for putting together this really great seminar series that I really enjoyed a lot and feel very honored to be invited there. So indeed, today I would like to talk about phonon-polariton lasers. So in a sense, turning into now we not only investigating those phonon-polariton, but also seeing how we can make them emit light. But before I do that, I'd just like to stress the seminal contribution of Keita Otani to that work for the experiments and growth of some materials, Martin Franke, who did the theory, and Bomeng also for some of the Raman experiment, and therefore, and of course, Matthias Beck for growth of most of the samples. So, if you think about emission, okay, the most natural thing to first consider is continuous emission, like from a light emitting diode. And what it is, of course, you take a two-level system and you couple it to a bath of bosonic modes, like plane waves, and those modes usually will have either zero or thermal population. And in general, the coupling of that two-level system to each one of these modes is very small. You have many of those, and as a result, you can compute the rate at which you emit spontaneous emission as using a Fermi's golden rule of the sum of the coupling to all of those modes. Now, how do you get from that to a laser? Well, you take the same ensemble of two-level systems. Each one will be this weakly coupled, and you, of course, try to invert it. And now you choose one mode of this bosonic collection of mode, and you manage to put it into a cavity in such a way that you have a low loss rate for that cavity mode. And now, if you think the total spontaneous emission that you have for the system, which is given by this n divided by tau spontaneous, you consider what is the fraction of that total emission into the mode that you have selected. And now if the rate at which you emit into that mode is equal or larger than loss rate of that mode, well, then you reach laser threshold. And now, of course, what happens there for those bosonic modes is the fact that you have out of your large collection of bosonic modes, you will have a large number of still unpopulated modes, and happily, you may have the one that you have selected will have a very high population. Not only you populate a lot that mode, but also the state of that mode will be a coherent state, and as such, it's a state that has also a low uncertainty, and is therefore good for interferometry. It's highly coherent. So it's, of course, something that typically you like. Now, obviously, so far you considered, of course, in terms of the laser is, of course, light emission and not other particles. But you, of course, you can easily think that, like photons, you can quantize vibration of a crystal, and those are bosons. And you could say, well, why don't I do also a phonon laser? And actually, it was demonstrated. And that was demonstrated, for example, in that very nice work by Keri Vahala in the group of Ted Hensch and Udem when he was visiting, where he basically used a single magnesium ion in an ion trap. And by exciting this pumping, if you want, that ion optically, he showed that when he was increasing the pumping, at some point, this magnesium ion started to have a coherent movement inside the trap, and that coherent movement increased with pumping, as you would expect for a laser. So this is basically a phonon laser in the sense that you're exciting a single mode. In that case, would just be a single mode of that ion in the trap. This, of course, happened at the frequency of the trap, which is about 70 kilohertz or so. Now, more recent, a very nice other work of a phonon laser was the use of an amplification of the motion inside a twisted trap. So there, you basically are trapping a nanoparticle, a transparent, typically a transparent silica sphere, inside a focused laser beam, and basically the radiation pressure of that focused laser beam is able to trap the particle. And now, by playing with the modulation of that trapping, you can basically also there create a motion of that particle, which is coherent, and which, in a way, again, you are able to controllably put this nanoparticle inside the trap as a laser. And then the nice thing also that they showed in that work was that they could measure the statistics of the motion and show that whenever they were below threshold, the intensity, or let's say it would be in that case not the intensity of the light, but the intensity of the motion was had a correlation function of 2 for the intensity, and that correlation function went down to 1 when they went above threshold. So these are the typical characteristics that you expect from a laser. Can also do that in a microcavity, again, work by Vahala and Kippenberg, where instead of taking an ion in an ion trap, here you take a mechanical mode of a microresonator. The force that you're acting on that mode is a radiation pressure of the light, which you coupled inside this microresonator. And again, you can show that you have the typical nonlinear increase in the displacement. And also they measured the line width, they measured the sharpness of that motion, and they showed that it basically had the same behavior as what you would expect in a laser. That means the line width decreases like 1 over the output power. The only technical difference is there they didn't start with 0. The mode was thermally populated before they turned the laser on, so it's more like a maser than a really a laser. Now, why all those experiments were shown at very low frequencies? The reason is quite simple, is because if you think about what is the condition to reach laser threshold, you have that the total pumping rate of your two-level system has to be equal to the ratio of the loss rate of your cavity divided by this beta, which is the fraction of the spontaneous emission that goes into your lasing mode. Now, this beta is inversely proportional to the density of boson mode. So if you have photons, for example, 1 over beta, which is proportional to that pump rate, is basically proportional to omega square, frequency square, divided by the light velocity to the cube power. So effectively, what you're showing here is that the threshold is inversely proportional to the cube of your light velocity. And of course, now if you think that you're going for a phonon rather than a photon, you basically have the problem that your light velocity becomes the sound velocity, and the sound velocity is much slower than light velocity. And that point was very well made, for example, in that paper from Jakob Kurgin, who studied that potential of using an intersubband transition as the two-level system and emitting now phonons going from an LO to a TO plus LA and making basically this LA-LAs. But again, the problem really there is that to reach laser threshold, if you think that you want to pump that structure not much more than what you would pump a semiconductor laser, well, you need to basically lower the frequency by the square root of the cube ratio of the light velocity divided by the sound velocity. And that gives you, therefore, a frequency in the tens of megahertz. So getting if you want, a very high frequency laser, phonon laser, seems to be very difficult because of that problem. But there is a way around. And the way around is not to think about making a phonon laser, but in some sense, trying to affect that phonon by coupling it to a photon. And I will not go long on this polariton because that has been really the topic of this whole series. So as you know, if you take an exciton in a bulk material, that exciton can recombine, emit a photon, that a photon can reabsorb and recreate the exciton. And if you have an infinite material and no loss, of course, this process will go forever. And therefore, if you diagonalize that system, you show that you can create this mixed excitation with the true eigenstate of your system. That true eigenstate is called the polariton. So it's a mixed matter and photon excitation. Now, of course, you can also create polaritons in 2D system by now flipping the system on itself by putting mirrors around your 2D system and by forcing the light to be periodically reabsorbed in a 2D system. And those are cavity polaritons instead of the body polaritons. Now, you can think of that polariton as being, as this nice picture of Cristiano Ciutti, as this kind of half photon, half excitation particle. And the nice thing, if you think in terms of a laser, is now that the mass, which of course is very much related to the density of state, and the density of state is basically proportional to the mass, then the mass can be in between the one of an electron and a photon. And in the case of exciton cavity polaritons, which were first demonstrated by, as you know, Claude Weisbusch and Arakawa, is the existence of this exciton cavity polariton is really demonstrated by this anti-crossing between the mode that corresponds to the cavity mode of that microcavity to the exciton mode of the quantum well, which is inside the cavity. Now, what you see here, be careful because those are a log ln scale. What you see here is the dispersion of that particle, and you see that you have uncoupled, you would have the exciton, which has a very heavy mass. So compared to the one of the photon, it basically increases for wave numbers that are in the 10 to the 100th of inverse micron. Whereas, of course, the photon, having a wavelength of order of micron, they disperse much more. And now what you see is when you couple those two excitations, you can get particles that have a mass in between the one of the exciton and the one of the photon, more closer to the photon. Now, the other, of course, mixed excitation that we will have discussed quite a bit is the phonon-polaritons. And the phonon-polaritons is a bit the same idea. You couple the mechanical motion of a binary alloy, like aluminum arsenide, for example, such that you have the polarization that resides between the aluminum and arsenic atom. That polarization, of course, when you have a vibration, couples to light, and because of that, you actually have again this anti-crossing here shown between the light that would propagate in the crystal. There were no phonons, and it couples to this mechanical excitation. And because of that, you have, as Hopfield showed already many years ago, that you have this lower polariton and the upper polariton. And now, of course, what is very important is that if you look now at that dispersion around the anti-crossing, you basically have the curvature, that means the mass of your, in that case, or the density of state of those excitation, which is now, of course, excitation. If you look at the upper branch, for example, you have definitely a more density of state than what you have for just the free photon, but the density of state is much lower than what you have for the pure photon. So you created your mixed particle. Of course, we've seen a lot of new work on this. You can image those phonon-polaritons. This is a work that was done recently in hexagonal boron nitride. And what I would like to see is whether we could make a laser out of those polaritons. So, of course, the laser, as we said, takes advantage of stimulated emission, and a priori you could do it with any bosonic particle. And so instead of stimulating a photon, think of it that you stimulated now a polariton. And if your polariton is a boson, then there's no real reason why it should not. And as we said, the threshold is achieved when the population of polaritons becomes larger than 1. Now, you have to be a bit careful because there are 2 types, if you want, of polariton lasers, in a sense that the polaritons, as I said, can be created out of a bosonized 2-level system, meaning if you take, for example, excitons, which are effectively more or less 2-level system, if you put a large collection of those excitons together, you can renormalize it and see it. You can basically create, either it's a bulk or a 2D polariton, but you basically can create a polariton. And now you can excite this polariton using an inverted reservoir. You have stimulated scattering into this polariton, and that polariton decays into photon, and that's what you basically measure in the end. And this is for example, was shown now some years ago, for example, in this paper by Jacqueline Bloch and Yoshima Yamamoto and Hu Deng, showing that you can create, depending on how you drive a microcavity containing excitons in quantum wells, depending on how you drive it, you can either have a polariton lasing or a photon lasing. And of course, the polariton lasing is characteristic of this mixed particle that contains this bosonized excitonic excitation, whereas the photon, if you want, is much more decoupled as material. Now, what we will look at is more like a harmonic polariton, because what we start from is not excitons, but we start with mechanical excitations, which are harmonic excitation that we couple to photons, and that system remains harmonic. And now what you need to do, because you can never invert a harmonic system, you need to, if you want, couple that system to a 2-level system that will maintain the oscillation. Or you can, of course, pump this using light. This is the other way of doing things. So, of course, polariton lasers have been demonstrated really long ago. If you think of optically pumped polariton lasers, the most useful or well-known ones is, for example, the ones that are based on lithium nidate that are also used to generate Terrace waves, and they rely on a optical parametric oscillator. So basically, you pump your system, you take advantage of the nonlinear, the chi2 of the material, and you basically create a Stokes and an Idler photons out of this. The Stokes is basically a photon. The Idler is a polariton because it has a very strong dispersion and it's very strongly coupled to the lattice vibrations. And this is basically, typically, you pump this using a optical pumping and current optical pumping, as you do in an optical parametric oscillator, and you pump this and you create spontaneously, you have a cavity that creates the Idler and the signal in Idler from this. And there you can use this, of course, to do lens spectroscopy. And now the question is, can we do this instead of pumping it optically? Can we use intersubband transitions? And the nice thing, of course, is intersubband transitions can be tuned to frequencies that can be close to the phonons or even below and above the phonons. They have this very short continuous emission for the optical phonons. They can be inverted as phonons. And the question is, having worked so long in quantum cascade lasers and trying to make them lays and it's always this optical phonon that gets in the way, you can also ask yourself, can you do something useful with an optical phonon? And now the HCU a few years ago, I mean, showed very nicely that the whole program of this Phonon-polariton laser actually could be carried again, like in the lithium niobate. You can do it again in a coupled well system. And what he used there was a gallium arsenide IGAS system, 3-level, and he basically showed that you pump and you basically get a signal and an idler. And that idler, he showed by plotting the dispersion of that idler had actually dispersion, which was a phonon-polariton dispersion. Now, what we ask ourselves is, can we do, in a sense, the same thing, but electrically? So you would generate directly the light. So what we used for that, we started from a very useful playground. And the playground is to play with this material system, which is the gallium arsenide antimony, indium gallium arsenide, aluminum indium arsenide system. And the reason it is an interesting system is that it's a heterostructure, so you can create quantum wells. The InGas is the well, and you can use either a barrier of aluminum indium arsenide or a barrier of gallium arsenide antimony. If you look now at the transmission as function of energy, sorry, the energy scale here is cut. But this is about 40, this is about 50 millivolts. So what is very interesting is that aluminum arsenide has a phonon, which is very well separated from both the gallium arsenide, the indium arsenide, and the gallium antimony. So all those phonons are there, and there you have just a single phonon, which is well isolated. And depending on whether you have a heterostructure that is InGas alinas, which is in the blue line, or whether you have one which is InGas gallium arsenide antimony, which is the red line, you will or will not have your phonon at exactly the same photon energy. And now the other interesting thing is that, as we showed here, you can do structures that are more or less similar, or very extremely similar in terms of their wave function, but that will either display the characteristic of the InGas gallium arsenide antimony or the characteristic of the InGas aluminum indium arsenide. And just to stress that this material system, the gallium arsenide antimony, was developed originally in Gottfried process. So the structure that we look at is a structure where we basically have a inverted system. We basically use indium aluminum arsenide barriers, and therefore inside those barriers you will have the optical phonon, and the whole structure is confined into a metallic cavity, which works a bit like a microwave strip line, but scaled down for the high terahertz frequencies. And now, as I said before, you have this well-isolated mode that is coupling to the light, which is guided into this metal waveguide. So what you have here, and that's important to remember, is you have a mixed mode, which basically has both photon and phonon character, both in terms of the material itself, but also in terms of the spatial extent of that mode. So of course, what we want to do with that is the emission of phonon-polaritons. And so again, to keep that in mind, what you have is a system where you have the stereophonons, which are coupled to the optical mode, and now you have this inter-subband transition, which is now coupled to this coupled system, if you will. And that is this two-level system provides gain at the photon energy where you expect to see this phonon-polariton. Now, the polariton mode, as I said, is one which has this mixed character, because when it is, if you blow up, this is a simulation of the electromagnetic wave inside the metal waveguide. So what you would expect normally is simply to have the field being basically homogeneous between those two metal plates and normal to the layers, which of course is the thing which is important also to satisfy the selection rule of inter-subband transitions. Now, what happens is, of course, each time the field is in the indium gallium arsenide, it is basically behaving as a photon, but each time it sees a barrier, you have this polariton character because you couple strongly to the mechanical motion there. And one way to show it is to show the fact that depending on, I mean, at the frequencies that are close to this resonance, you see that we have the energy density, which peaks inside the barrier material. And that actually, what is very important to see here, it has some consequences also, is the fact that, you see, the phonon is actually much more confined to the electron. The phonon is basically inside that barrier, whereas the wave function of the electron extends over many quantum wells. I'll come back to that. So how can you show now that if you make this thing laser, how can you show that you have a laser, and how can you show that it is a Phonon-polariton laser? So what we can always do, of course, is do like everyone does in, you know, polariton photon laser. You can measure the photons that are emitted by the cavity. And so what we saw in this device is the fact that when we when we drive the device below threshold, we see emission. And we see two peaks because the light inside the Rastranand band, limited by the LO and QO frequencies, is blocked. And we basically see emission, which is on both sides of the Rastranand. But when now we provide enough gain, we suddenly see a abrupt increase in the light emission, is what effectively what you expect from a laser. And you see light emission very, very close to this Rastranand. Now, you see only one threshold, and you see lasing only in the upper branch. We don't see lasing at lower frequencies. And that is because, of course, there is basically no gain. This is, of course, important. Now, how can you prove that this is a polariton? Well, one thing that you can look, and it's definitely characteristic of a polariton, is its dispersion. So what you can try to see is look at the anomalous dispersion of that polariton. So how can we do that? Well, that's where it's good to have someone who has patience and grow a lot of samples, because you make many devices, and these devices, they will span this frequency range and try to see how does the laser changes when you go from emitting at that frequency to that frequency. And you can already guess that here you have a very small curvature, you have a much larger curvature, and so you should see something happening. And indeed, those are all lasers. Those are, each one is a different growth, which is tuned for a different frequency. And you see that here, if I start from the kind of the highest frequency, you see that those lasers are all the same length. So the spacing of the mode should simply be C over 2 and L. But now N is the group index, and the group index, of course, is connected to the curvature of that, contains actually the curvature of that curve. And so what you see is that the spacing of the mode becomes narrower and narrower as you go closer to this point here. And you see that the group index goes from 4.5 to almost 10 when you're very close to when you're actually at the lowest frequency. And just to make sure that we don't have that, it's not an artifact, we also can compare that to the laser where you do not have any aluminum arsenide phonons, the one based on antimony, and that laser based on antimony has now a group index, which is basically constant for this whole distance. The other way to check is actually, of course, the nicer way would be to, can you probe directly the phonons? And how do you usually measure phonons? One very nice way of measuring phonons, of course, by Raman spectroscopy. So you excite at a completely non-resonant frequency, and you collect the light which has been scattered by this phonon. So how can you do that experimentally? Well, the way to do that is to basically do a Raman experiment. So you take a green laser, you send it to your device, which is sitting in the cryostat, and you, because I forgot to say, but this device operates at this point, the first measurement actually were all done at cryogenic temperatures. And you look at the facet, And now what you look is for scattered light that will be coming back, and you collect the light back into a grating spectrometer after, of course, going through a notch filter that will remove the basically pump laser component. So effectively, what you do is you excite, and what you could hope to see is either a Stokes, that means an emission, or an absorption of photon, and an so-called anti-Stokes emission. Now, first thing to say is, of course, if you're working at low temperature, which we are, you would expect only to see that line, because the other line, if you had only thermal phonons, you would only expect to see the Stokes line, because, of course, you have no population of phonons inside your system. So this is the spectrum that you see if you do this experiment at below threshold. The device is pumped below threshold. What you do see is, okay, we've cut the laser output, but what you see is the indium arsenide phonon, the gallium arsenide phonon. You do not see the aluminum arsenide phonon, which should be around here, because you have only 6% of aluminum inside the barriers, and therefore inside the whole structure, so it's a weak signal stream. But now, what of course is quite dramatic is the fact that when you go above threshold, you see that all the other peaks basically remain the same. The whole spectrum remain really the same, except that now you see an additional peak at 48 milliectron volt, which is exactly, of course, the photon energy that you're collecting with your far field experiment. So you basically have a one-to-one frequency connection between that peak and the photon energy that you see in the this Raman experiment as the one that you see in the optical experiment. Now, you may also notice that within experimental error, we have the same intensity of the Stokes and anti-Stokes peak, which means that our number of excitation that we collect, that we have inside the material is very high and is very large, and therefore the probability of absorption or emission are basically equal, because they are proportional to 1 plus 1 is, this one is proportional to 1 plus n, this one is proportional to n, and the ratio between 1 plus n and n in that case is very close to unity, because we have lots of polarities. One thing that I still must mention is that this geometry is highly inefficient. It's highly inefficient because imagine you absolutely do not satisfy case selection rule. What you have is you have a green photon coming inside, and you're collecting a green photon outside. So you basically have a delta K between the inside and between the incident and backscattered photon, which is basically twice the photon energy of your pump laser, and the excitation you're basically probing is one which is very close to K equals 0, because it's this upper polariton. This upper polariton has a K which is even lower than the K of the photon. So it's highly mismatched, and the only reason why you can still see something is because the light is very strongly absorbed inside the material, and therefore, you basically benefit from not satisfying, you relax the case selection rule in that way. So you can also look at the intensity of that Raman peak as a function of injected current, and you see that that Raman peak very much follows the intensity of the light that you collect. You can also do the same experiment using a laser that has no aluminum arsenide inside, and you see that we almost see no emission. We also can check the polarization selection rule. There I will not go into details, but by basically choosing properly the polarization of your green laser and the polarization of your detected Raman signal, you can show that what you see is only when you have the proper selection rule. That means when you have if I remember well, when you have only the TE and TM. So you satisfy selection rule, so it really, again, agrees with the fact what you expect. which is that it is a phonon-polariton. You can also do a last check, which is if you take a high-power terahertz quantum cascade laser, do you see the Raman emission? Well, answer no. You would expect a signal here in that laser, which emits still quite a large amount of power. You would expect the signal here, and we don't see anything. And the reason is that in that laser, you're very photon-like, and your matter part is very small. So, just a few words about how can we, if you want, model this, and how can we sort of predict the characteristics of that laser. And it's not so easy because, I mean, it was not totally obvious to us initially how we could treat that system. And the idea was, in the end, was to basically create, first of all, a phonon-polariton, and basically diagonalize the system between the few phonon and optical mode. It has been done many times. It's basically what, in other words, this is the Hopfield program, if you want. And now, then couple those polaritons to the intersubband transitions. And we did that using the power in the dipole gauge. And, well, to make a long story short, because not go into all those details, it's all in this PRB that we published. Basically, what of course is nice is that we can express the phonons by a polarization. And so we effectively have the free field using a displacement. Well, of course, free, we still have the background dielectric constant that is inside, but all the other two matter part, which is the intersubband transition and the phonons, we treat them using polarization. And the light matter is right. And then you see that here we have two coupling between light and matter. One is the coupling of the intersubband polarization with the electric field, and the other one is the intersubband with the phonon field. So there, in the end, the program was we diagonalize the system which contains the radiation, let's say the matter and the radiation part, with the light matter coupling of the cavity with the phonon-polariton basis, and then we look at the coupling of that system with this coupling Hamiltonian. And we couple that using the Hopfield coefficients that are characteristic of the photon and the phonon. So in the end, what you basically, the threshold condition, if you expand everything, you get this type of interaction Hamiltonian, and you can write the Fermi's golden rule. And the Fermi's golden rule now contains scattering onto this would be the just the light matter coupling, and this would be the phonon coupling. And then what is, if you want, what is tricky, well, what you have is of course an inversion that drives the system. So as function of energy, what changes, if you want, is the component of the photon gain, the component of the phonon gain. It's actually never phonon gain pure, it's a coupling. And of course, what you have also to take into account is that the lifetime of your particle, the polariton, changes depending on the Hopfield coefficient, because the phonon lifetime and the photon lifetime are not the same. And in that frequency range, it turns out that the phonon has a longer lifetime than the photon. And that is because you are dealing with this heavily doped material and this rather lossy metals. And that, of course, is if you want, this is why the loss rate is actually privileging more, if you want, having something which is more matter than photon. So details in this PRB. Sorry. Yeah, okay. So just going back a bit to more qualitative more qualitative characteristic of that system. So we have a system where we have polaritons. They are not very strongly coupled because the Rabi frequency is something like 2 electron volts. Of course, you can have much larger couplings in different systems. We still are, if you want, in the, it corresponds to 4% of coupling, but the ratio of this coupling to the broadening is more or less a factor of 10. So in principle, we should be, I mean, either in a strong coupling or close to a very strong coupling regime. Now, of course, you have to be a bit careful because that statement only is valid when you compensate part of the gain, part of the loss with gain. So it is a bit to be taken with a grain of salt. And depending now where we lay, when we were actually studying that device that had those series of devices, when we were moving along the dispersion curve, what we see here is that the phonon fraction and the photon fraction change quite a bit. And so at the largest, let's say at the shortest, at the longest wavelength, so at the lowest energies, when we were more phonon-like, we actually had polaritons that were more phonon-like than photon-like. So in a sense, this is why I think it's very justified to go at a phonon-polariton laser, because the particle that you have in the end is heavily, has more than 50% of matter. So this is one way of emitting light using phonons. There's proposals that our chairman is actually working on, which is also very exciting. You can also use gallium nitride phonons. One thing which I still want to discuss a tiny bit is this two-component to the gain, because this is really quite interesting. The coupling, as I said, has this, on one hand, you have the electric field, which couples to the electronic wave function. And now, of course, spatially, the electric field takes a whole cavity, and the wave function is a few hundred angstrom long. So that size of that term, if you want, is roughly limited by the electronic wave function. Now, that in a sense is by essence a smaller term, because the phonon displacement field is the one which is basically the length of the barrier, and which is much smaller than the length of the electronic wave function. So this term is by nature much larger than that term. But now, of course, first of all, you have to be careful that in the end, you have to sum the two, and so you can have either positive, let's say you can have constructive or destructive interference between those two terms, depending on where you are. And actually, it turns out that you have typically constructive interference when you're above the upper polariton, and destructive below. But also, so if you call that the photon and the phonon gain, but of course, the ratio of those two terms will now depend quite a bit on the material that you choose. And especially if you have a material which has a large mass and very strong phonons, like zinc oxide, the balance between the strength of those two components may now be balanced much more towards the phonons. And this is a computation that's unpublished by Martin Franke. He showed that in this resonant tunneling structure based on zinc oxide and zinc magnesium oxide, for example, if you look at the peak of the gain, which in that case would be about 80 electron volt, the non-photonic gain is larger than the photonic gain. And that is simply because now you have a very strong phonon, and in a sense, you have, of course, much shorter wave functions because you have a much larger mass, but you still have and at the same time, a stronger phonon polarization. So in the end, if you look, you have this gain which is dominated by the non-photonic component and a very large matter component of the particle, that even larger, if you want, of the Phonon-polariton that you're exciting. So I think this is very interesting because in a way, in the context of this, of course, first demonstration of this electrically pumped Phonon-polariton, we've shown that using a QCL based on InGaAs aluminum diamondsonide in the Raman band. But I think it's really, we still have not fully leveraged on the really interesting aspect of that device. First of all, is that because the phonon part is confined in such a small volume, you can really think of now making really way smaller cavities, because then you rely on the confinement of the phonon itself. Of course, if you were able to provide lower losses, you have higher temperature operation, lower threshold, but also it would be a very interesting way of using 2D materials and our very heavy materials to still make lasers in this low 100 melectron volt or lower photon range. So with that, I would like to thank you for your attention and thank again the members of my group who participated and contributed to that work. And well, welcome questions.
Well, thank you, Jérôme, for the amazing talk. I knew already the basic material, but I still learned a lot. Before passing to the questions, allow me to remember to everyone that the recordings of the first season are available online, and I just posted in the chat the link. I'm doing this because multiple people keep writing me to ask where the videos can be found. The videos of this season will be also uploaded on the same website in a few weeks. Okay, now we can start with the questions. In order to ask questions, you can use the Q&A button on the bottom of your Zoom interface. Either you write your questions in full and I will read them. In such a case, if you want me to read your name, please write your name explicitly, or you can just write questions. I will unmute you and I will let you ask the questions. I will ask the first question. The last bit about the gain of the two terms, I find it very interesting. Of course, didn't have much time to think about it, but what happens if, because you told that in the material you're using, one of the type dominates, but moving toward other materials, they can be balanced. When you arrive at a perfect balance, what do you obtain? A lacing only in some of the polariton modes accordingly to the relative phases of the fields, or?
I think, to 0th order, you simply get more gain. It's a term that you can take advantage. It doesn't have also, of course, that term has other selection rules than the ones that, if you want, the photon gain, because now it's really, the shape of the wave functions is very different. And I'm not sure if you can really, of course, especially in that picture where we basically simply say, okay, that two-level system really drives the polariton system. And of course, if you have stronger phonon, that polariton system will be even more robust and will behave even more as a polariton system. I don't expect, if you want, much new physics of the polariton laser itself coming from that gain. It's just, to me, interesting because it gives you a new knob that you can optimize for materials that in essence are not very attractive initially for intersubband gain because they have this very heavy mass and low dipoles.
Just that the different polariton modes you have will have different relative phases of the fields. So they will respond differently.
Absolutely, absolutely. So you have exactly, you have this constructive or destructive interference because you square the sum of those two terms. Absolutely. Yeah.
Okay, we have a question from Janko. Janko, you should be able to talk now.
Okay. Sorry, can you hear me?
Yes, we hear you.
Yeah, okay.
Hey, Janko.
Hey, hello, yes, very nice talk. Thank you. And I was actually typing my question. So the question was, is there a fundamental reason of not using the phonon in the quantum well material? And would it be better because of the larger overlap with the electronic wave functions?
It's a very good question, of course. I think the issue is really the fact that each time you add this polytonic material, you of course also add if you want to increase the density of state that you have, and therefore you also increase the loss. I mean, the loss rate will increase because you have more material that can dissipate now. So initially, and we never published that elsewhere than in this archive, this first version of archive paper, we basically had only one buyer that was aluminum arsenide. And that was, we never finished fully that study. And we first, because we were very much afraid not to be able to show Phonon-polariton lasing because of having too much of this, if you want, lossy material. Now, the next step, which is the one we published, was material where we had actually all buyers had this that Phonon-polariton. Now, for sure, you make a very good point in a sense that you may want perhaps to have polaritonic material all around the upper and lower wave function of your material, but for sure the injector you don't benefit much in having it with phonons, because that will simply add passive, if you want, those will not increase your coupling. So the phonon gain will increase, as you said, by having more by having more phonons around the wave function of the upper and lower state. But if you want the injector, where you have just thermalization of the carriers, will not benefit from having, in that sense, more phonons. So the best arrangement would be perhaps the one where you have lots of phonons just around the upper and lower wave function, and then having a fully passive, if you want, injector.
Thank you very much.
Thank you. Do we have any other question? Yes, please.
Okay. Hi.
Oh, hi, Hal. Nice. Thank you.
Hi, Jérôme. I also have a question. I mean, in this system, I'm very nice talk, by the way. In this system, there are three kinds of bosons, right? There is the phonons, the intersubband polarization, and the photons. And now, if I understand correctly, you have strong coupling between the intersubband polarization and the phonon field, but you have weak coupling with the photons, right?
No, it is, I consider a strong coupling between the photon and the phonon field, because that's what gives me this dispersion, you see. Mm-hmm. And weak coupling to the intersubband, because let's not forget, when you have a laser, an intersubband laser, you can only invert very little carriers. Mm-hmm. That's why the coupling from the carrier, you see, the fact that we see these polariton upper and lower polariton branches, that comes from the coupling of the photon field and the phonon field inside the barriers.
Okay, so you really have the situation that you have a microresonator which gives rise to the strong coupling, as it has been also observed, I think, in some kind of nanocrystals, right?
Yes, perhaps. Yes, okay. Yes. In a sense, you really create gain in a system that has a dispersion of a polariton, which is what I was trying to, that's what I call this harmonic polariton, because the system, the polariton itself cannot be inverted. Whereas if you think, if you pump enough of the excitons, you can sort of invert the system.
And a strong coupling between the intersubband transition and the photon field is probably not possible, because you have to go to stay at low carrier densities.
Because it's so hard to, you would need, first of all, it would be, of course, if you provide this with, nothing would prevent you in principle to modify, if you want, the dispersion by adding an additional quantum well somewhere with carriers that would give you, if you want, an intersubband. Now you could make phonon, like actually Carlos Sirtori and Jaco Todorov did. couple both inter-subband phonons and clarity, you could in principle have that and add gain somewhere. And then you could engineer maybe even further the dispersion using this. But of course, the problem is always you tend to add loss. So this is, of course,
you need much more absorption to get that.
Exactly. The danger is that you have too much absorption and you don't get it.
Okay, thank you very much.
Thanks.
Any other question? Well, if not, I think we can all thank Jérôme again for the wonderful talk. And I thank you all for your attention, and I hope to have you with us again next week for the talk by Dmitry Basov, who will present some results on polaritons in van der Waals materials. Thank you again, and see you next week.
Thanks, Veronica.